Before we can discuss the cloud chamber, we must quickly discuss clouds. Clouds form from any vapour which is present in an atmosphere once a certain condition has been met or surpassed. This condition is called the dew point of a vapour, which is different for different vapours and also varies depending on the immediate conditions. The dew point can also be considered the saturation point of an atmosphere. Once an atmosphere is saturated, it will not be able to hold any more vapour, and droplets will begin to form. This is a video of clouds forming in the atmosphere. We can clearly see where the saturation point is being reached and exceeded, clouds simply forming out of a previously clear sky. Experimental observations tell us that droplets will condense on a small object, usually called a site, before they spontaneously condense out of the atmosphere. It is for this reason that aeroplanes travelling very high up leave exhaust tracks in the sky. These are not actual clouds of exhaust from the aeroplane engine, but where the water vapour in the atmosphere is condensing onto the particulate exhaust particles. To explain how a cloud chamber detects radioactive decay particles, we must have a quick look at the thermodynamics of cloud formation. Rather than try to fit in a full description of the thermodynamics required, and also to avoid a lengthy derivation, the following equations will simply be quoted. The first is the Kelvin formula for a droplet forming on an uncharged site. The second, for the same conditions, a droplet forming on an electrically charged site. Notice that these are the same relationships, but the second expression has this term, which shows that cloud formation occurs preferentially on a charged site. Once again, the dynamics used in the derivation of these equations is beyond the A-level course, so there is no need to worry about understanding them fully, just that clouds form around charged sites at a lower saturation than required for formation on uncharged sites. So, to summarise, droplets preferentially condense on a charged site, and therefore any charged particle is detectable by using a cloud chamber. It is important that clouds form on charged sites at lower saturation levels than for uncharged sites, because if we can engineer conditions within a cloud chamber where the vapour is at a saturation sufficient to condense on a charged site but not on an uncharged one, then we can easily detect charged particles. The passage of a charged particle through such a vapour will produce a long, usually thin cloud marking its passage, also called a contrail. It should be noted that clouds forming in a cloud chamber are not produced by vapour droplets condensing onto the radioactive decay particles themselves. The droplets form on the ionised atoms, or molecules, left in the wake of alpha and beta particles. As the particles travel through the chamber, they will ionise atoms and molecules as they go. Alpha particles, with their large cross-section, will ionise a great many more atoms than beta particles in the same distance. Therefore, we would expect more droplet condensation along the path taken by an alpha particle than a path taken by a beta particle. It is by using such distinction that it is easy to distinguish between different types of particle within a cloud chamber from the clouds that are formed. Following our discussion of what can be detected within a cloud chamber, we will now look at some examples of a cloud chamber in action. This is an example of what alpha particle tracks look like in a cloud chamber. The decay process we are seeing is the decay of americium-241 to neptunium-237. The tracks we see are relatively thick, although not particularly long, as we will see later. We can also see that the paths taken by the emitted alpha particles are distributed evenly around the source, with no particular direction preferred. By moving the source behind a paper screen, we are able to clearly see that the paper absorbs all of the alpha particles which strike it. This is an example of what beta particle tracks look like in a cloud chamber. The decay we are seeing is a decay of cobalt-60 to nickel-60. If you keep your eye on the area indicated by the arrow, it is possible to see a typical ionization track left by the passage of a beta particle. As we can see, the trails left are fairly wispy and faint, just as we would expect for a highly penetrative particle. Now, if the beta particle source is moved behind a paper screen, we can still see some tracks left by beta particles. Again, keep an eye on the area indicated by the arrow. When the source is passed behind the LED screen, we can see no tracks, just as we would expect. The dense material is absorbing all of the beta particles which are being emitted. That was the beta decay from cobalt 60 to nickel 60. As we would have expected for more penetrative particles, the contrails were much thinner and more difficult to see than the alpha particles. This highlights the relatively small cross-section of a beta particle when compared with an alpha particle. Now, before we conclude this discussion of cloud chambers, we must mention the background radiation experienced every day by everyone on the planet. Part of this radiation is known as cosmic rays, and aside from being interesting to physics, poses no particular threat to anyone. The term cosmic ray is a bit of a misnomer. They are actually charged particles, bombarding the Earth from all over space. They are emitted from stars, and as such, the majority of cosmic rays striking the Earth are from our Sun. The cosmic rays energetic enough to pass through the Earth's magnetic field interact with the upper atmosphere in such a way that converts a large portion of their energy to a large number of particles. These showers of particles rain down through the atmosphere, some being absorbed and others reaching the ground. What we would expect to see in a cloud chamber, therefore, is evidence of a very large variation in the track formation direction, the thicknesses of the tracks, and the different lengths of the tracks. We might also expect to see some ionization tracks which are curving. This is not the particle scattering off vapor molecules, but the particle experiencing a Lorentz force strong enough to curve the path of the particle. From this we can deduce that the particle has a small mass and a large charge. This is an example of what the ionization tracks produced by cosmic rays in a cloud chamber. As we can see, there is the expected variety of track lengths, thicknesses, and clearly there is a random distribution to the direction the contrails are forming in. If you watch the end of the arrow closely, it is possible to make out a faint but clockwise curving contrail. This is one of the particles produced by a cosmic ray being subject to the Lorentz force due to the Earth's magnetic field. So due to the thickness of the contrail, we can deduce that it is a strongly charged particle, so ionizing a wide track of molecules. In the case of the cosmic rays which are diverted towards the magnetic poles, when they interact with the upper atmosphere, they do not have sufficient energy to convert into mass. Remember, when a particle is created, its antiparticle must also be simultaneously created, so that only very high energy collisions can produce particle showers. Instead, the lower energy particles can only ionize the atmospheric components, and so after the collision, the electrons can recombine with their atoms, releasing energy. This energy is electromagnetic radiation in the visible spectrum, usually a green color. This is the source of the aurorae. Because they are such beautiful physical phenomena, mentioning the aurorae can only properly be followed with a video of them, in this case taken from the International Space Center. This concludes our discussion of radioactive decay particles and how we can detect them using a cloud chamber. I hope you found it useful. Thank you for listening.